All right, does anyone have any questions now that we've started recording? Great, so I want to address a couple, before I begin the lecture, I want to address a couple questions which came up in the Discord, and then also I want to correct a slight mistake I made in the last lecture. So first of all, there was a question about what precise categories of sheaves FP-APF descent gives an equivalence between. So I think the way I stated the theorem the last time was that if X is a scheme, then there was an equivalence of categories between quasi-coherent sheaves on X. And we can write that in the following way. We can write quasi-coherent sheaves on the small Zariski site of X, right? So that's just the usual notion of a quasi-coherent sheaf. And the way I stated things was that pullback gives an equivalence between this, between N and quasi-coherent sheaves on the small étale site. And then I think maybe verbally, I said it also gives a equivalence between this and quasi-coherent sheaves on the small FPPF site. So let me just remind you, the small FPPF site, the objects were flat X schemes and covers were collections of flat X schemes, which are flat finitely presented X schemes, and covers were collections of such which are jointly surjective. Okay, so these are all equivalents of categories, and this is more or less just a restatement of what, well, the equivalence between the first category here and the last category is more or less a restatement of what FPPF descent says. So someone in the Discord asked, what about the big sites? And okay, you can actually make a statement there. So the category of quasi-coherent sheaves, meaning sheaves which are like locally quasi-coherent, on the big sites are not going to be equivalent to the usual categories of quasi-coherent sheaves. But what you can say is you can look at the big Zariski site of X. So here I'm using capital Z to tell you that that's the big site. So just a reminder, what is that category? Well, objects are just all X schemes, and then covers are Zariski covers, right? So you're not just looking at Zariski opens of X as objects of the category. Well, quasi-coherent sheaves on this site are the same as quasi-coherent sheaves on the big étale site of X. And these are the same as quasi-coherent sheaves on the big FPPF site of X. Okay, but these two rows, these triples of equivalences, like the quasi-coherent sheaves on the big Zariski site are not the same as quasi-coherent sheaves on the small Zariski site, right? So it's worth thinking about this, but it's some kind of subtle difference between these two settings. So let me just give you an example. So what is a quasi-coherent sheaf on the big Zariski site? It's just a quasi-coherent sheaf on every X scheme. And like morphisms between various pullbacks. But like they don't have to be, like you don't have to, it's not picked out by what sheaf you have on X itself. Okay, are there any questions about this?
Is this going to have a big effect on cohomology groups down the line?
This won't matter. It won't matter at all. Yeah, I mean, somehow when you compute cohomology groups, that only captures covers of like X itself. It really won't matter in the slightest. Yeah, this is just a technical point. This, like, you can completely ignore this for the rest of the class. All right. Like somehow if you have two spaces, like X and let's say X and some X scheme Y. Let's just say, for example, like Y is X times the affine line. Like there's no scheme with an étale map to both X and X times the affine line. So somehow like those objects don't really see each other at all in terms of covering. It's like there's no way to pass data between them. All right, so the other thing I wanted to mention is a small correction. So I think when I was discussing the failure of FPPF descent for schemes, so the fact that the pullback functor wasn't essentially surjective, I claimed that I think étale descent data for schemes is the same as an algebraic space, and that's not quite true. So what is true is that étale descent data for schemes gives you an algebraic space, but they're not literally the same thing. So you can present an algebraic space in a way that looks kind of like descent data, but it's not like literally descent data. So if you have questions about that, you should come to my office hours, or send me an email, or just ask after class. And maybe one more remark. So I usually have office hours on Mondays at 10 a.m. I did not yesterday because of Labor Day. So I'm happy to add extra office hours this week if anyone wants them. So if anyone wants additional office hours, send me an email and we'll do it. Otherwise, we'll continue as usual a week from yesterday. All right. Are there any questions before we move on to the material for today? All right. So what's the goal today? So the goal is to fill in some of the gaps I've left, and finally actually define atal cohomology. So today we're going to define the object that this course is about. So what's missing? So what's missing is the following claim. So it's that the category of abelian sheaves on the atal side of a scheme X is an abelian category and has enough injectives. Okay, and once we have that, then we can just use the usual formalism of derived functors to define atal cohomology. And just a reminder that once we have that, the definition is going to be the following. We'll define the atal cohomology of our scheme X with coefficients in, let's say, the sheaf Z mod LZ, just to be the derived functors, the right derived functors of the global sections of our sheaf on X. And so we've already constructed this sheaf Z mod LZ. What is gamma X atal Z mod LZ? Well, you just evaluate it on the object X of X atal, and then we're going to take the derived functors of that. Sorry, was there a question? No, okay. Cool. And the crucial ingredient in at least proving that this category is abelian is going to be the following. So it'll be the following theorem, which I stated at the very end of last time, which is that if tau is any site, then the forgetful functor from sheaves on tau to pre-sheaves on tau has a left adjoint. Okay, and just a reminder, I'm not going to prove this theorem in full generality. I'm going to prove this for the atal site. Okay, and I think I do suggest you try to look up the proof of this theorem, and there are many places you can look. If you just Google sheafification for sites, you'll find it, because it's a cool proof, but there's a softer argument for the atal site. I mean, this is some purely categorical statement. Okay, so let me just briefly make a couple remarks about this. So first of all, the left adjoint is going to be called sheafification. Okay, and what's this functor? So maybe can anyone describe this functor, forgetful functor, for me, just so I can make sure y'all are following?
I mean, it's just going to be the same functor, underlying functor, like we just don't care about.
Yeah, so a sheaf is a functor, you just forget that it's a sheaf, you send it to the same functor. So this is actually an inclusion of a full subcategory. That's exactly right. Okay, so before giving the proof, we need a couple operations we can do to sheaves. We need to understand how to manipulate these, and basically we're going to learn enough about sheaves that we can imitate, in some sense, the usual proof that sheafification exists on a topological space. So just a reminder, how do you how do you do that? Well, you construct this object called an espace étalé out of the stalks of your sheaf, and then you of your pre-sheaf, sorry, and then you define the sheafification to be sections to that space, right? That's one construction of sheafification. So the construction for a general site is actually, there's a very cool alternate way of doing things, but we're gonna do enough to like understand what a stalk is to make some kind of functory version of an espace étalé. That's gonna be the idea of the proof. Okay, so we need two things. So first of all, we need to understand how to take push forwards. Okay, so I'm now gonna construct for you an operation you can do to a sheaf. So suppose F from tau 1 to tau 2 is a continuous map of sites. And I think we're now catching up to where we were at the end of last lecture. But I just want to recall this because we're going to be using it a lot. So can anyone remind me verbally what it means to be a continuous map of sites? Maybe I won't rewrite the whole thing today since we did this at the end of last time. Verbally or in chat, it's fine.
The functor in the opposite direction, preserving products?
Yeah, so it's a functor from tau 2 to tau 1, which I called F inverse. And it preserves fiber products, and then it has one more property. It sends covering families to covering families. So what you're supposed to think is that if you have a cover of an open set and you take the preimage of that cover, that's a cover of the preimage of your open set. Is everyone cool with that? Sorry, I'm looking off to the right, by the way. The chat and the list of names and so on is on my second monitor. All right, so what we did is we defined if for G, a sheaf on tau 1, we defined the following: F lower star of G to be the following functor. It sends an object U on I guess tau 2 to G evaluated on F inverse of U. Oops. And just a reminder, so F inverse was the functor going the opposite way. And so U here is an object in tau 2. So F inverse of U is an object of tau 1, and we can evaluate G on it. Okay, and the exercise, I think I asked you to do it at the end of last time, and I will again ask you to do it, is that this is actually a sheaf. Okay, so let's talk about some examples. Okay, first of all, can anyone give me an example of a map of sites?
Just a map of schemes, like just pulling back.
Yeah, exactly right.
Right.
So suppose I have F from X to Y is a map of schemes. Then we get from this a map, which I'll also call F, from the étal site of X to the étal site of Y. So I think Ali told us what that map of sites is, but maybe Ali, can you tell us again, or can someone else explain how to do this?
Well, yeah. So if I have an automorphism going to Y, I'm just going to pull it back along X.
Yeah, exactly. So you send it to U times X over Y. This is now an X scheme. Exactly right. Okay, so that's a functor. It's just taking the fiber product with X. It sends étal things to étal things, so it's an actual functor between these two categories. And then you have to check that it sends fiber products to fiber products and covers to covers. Okay, so we've now defined. So from this we get a functor F lower star from sheaves on X étal to sheaves on Y étal. All right, so let's talk about some examples of this. So here's a good example of a map. So suppose K is an algebraically closed field. and we have a map, which let's call X bar, from spec K to X. All right. So maybe I'll call it iota X bar. So you just have to think X bar is like a geometric point of X. That's where the notation comes from, and iota is its inclusion. Cool. So can anyone describe for me sheaves on spec K at all? I think we had an exercise about this. So maybe, can anyone tell me what is the category of sheaves of sets on spec K at all?
Is it just going to be like sets?
It is just going to be sets, yeah.
Yeah. So the point is, what is an ATOL cover of spec K? It's just a disjoint union of copies of spec K, right? That's what a ATOL K algebra looks like when K is an algebraically closed field. Okay. So now suppose I've told you the value of your sheaf on spec K. Well, now I know what it is on any disjoint union of copies of spec K because there are a lot of sections from spec K to a disjoint union of copies of spec K, right? So you can cover any disjoint union of copies of spec K by spec K itself, or by a bunch of copies of spec K itself, just by definition. Okay, so that tells you the value of your sheaf on spec K determines its value on the whole category. So you should, if you haven't done this exercise, you should definitely do it. Okay, so now can anyone tell me, so given a sheaf F, which is a sheaf on spec K et al., and that's just the same as a set, can anyone describe for me the push forward of this sheaf? So what do we need to do? So given some u to x, we need to compute its value. So how do we do that? Yeah, so this is defined to be the skyscraper sheaf with value that set. So how do you evaluate the skyscraper sheaf? Yeah, so I'm going to say that in a second. This is the definition of the skyscraper sheaf. So how do you evaluate that sheaf on some ATOL X scheme?
If like the image of the point, if the image of my ATOL morphism contains the image of that point, I'm guessing then I'm just going to be that set, and if not, the empty set.
Yeah, so that's not quite right actually. So that's why that's a very good guess. Yeah, it's not quite right. So what happens? Let's try an example. So let's actually just use the definition. So what does the definition tell us? So it tells us that it's F evaluated on U times over X with this point X bar, right? So what is that fiber product? Yeah, exactly. So Sarah has the right answer. We have to care about, sorry about that. We have to care about the number of preimages of the point. So this is F evaluated on a disjoint union of copies of spec K, where here this is the number of preimages of X bar in U. Okay, and then this is just, well, we can now use the sheaf condition to evaluate this. This is the product over the number of preimages of F of spec K. Okay, so the definition, which Sarah guessed in chat, is that iota X bar F star is called a skyscraper sheaf.
Does the condition that the cover be finite presentation limit the size of the sets you can have here? I mean,
yeah. So an ATOL morphism is always quasi-finite, so they're always finite.
So when you say the category of sets, you're not talking about the vastly uncountable numbers of sets. The sets are all going to be finite ones or such things.
No. So here I'm talking about sheaves on this category. So
Yes.
a sheaf can have a sheaf in sets can have any value. There's no limit on that. So this category of sheaves is not a small category.
Okay.
Yeah, but the cover itself is the covers themselves are bounded. So here we're taking a product over a finite product, but it's a finite product of possibly very big sets. Okay. So this is an example. Let's see. I think we're gonna later see a lot of other examples of push forwards, but in general, it's kind of hard to compute a push forward beyond the definition. So maybe I won't say more than that. So let's talk about pullbacks. So we've defined pullbacks. So we've defined push forward. So let's define pullbacks. Okay, and we won't actually be able to define pullbacks yet. And why is that? Well, if you think about the usual setting of sheaves on a topological space, to define a pullback of sheaves, what do? You take some inverse limit, and all that to compute the value on an open U, and all that does is it gives you a pre-sheaf. That pre-sheaf is not typically a sheaf, and then to define the sheafification, you sheafify that object, and we don't know how to sheafify yet. So we actually don't yet have the technology to define pullbacks in general. But what we can do is we can define pullbacks to a geometric point. And the reason why is just that any pre-sheaf on spec K et al. is actually a sheaf. And we already, well, sorry, that's not quite right. A set is just the same thing as a sheaf. It maybe is the right thing to say. So it's very easy to sheafify over a geometric point. Okay, so let's define this. So suppose again I have iota x bar from spec K to X. And here again, K is algebraically closed. All right. So what I'm going to define is just a set. I'll call it fx bar. So this is going to be a set. If you'd like, you can consider it as the pullback along this inclusion of a sheaf F, or here F a sheaf X et al. But here, when I write this equality, I mean, so this is a set, and this is a sheaf on spec K et al. So when I write this equality, I'm using this identification from before between sets and sheaves on spec and algebraically closed field. Okay, so what's the definition? So we just copied the definition from usual sheaves. So I'm going to define fx bar to be the following, I guess, direct limit. Sorry, I think I said inverse limit earlier, but it's actually a direct limit. So it's the inverse limit, or the direct limit, sorry, over u comma u, and I'll write a diagram in a second of f of u. Where here, what is the limit taken over? Where the direct limit is taken over over diagrams like this, over diagrams. So here we have x bar including into x, so that's what I call iota x bar. Now we're going to take an open of an étal u over x and a geometric point of u living over x bar. So this inverse limit is taken over pointed étal x schemes. So here this is étal, and this is a geometric point. Okay. So note, for example, this works totally, like we don't have to be working at a closed point. Like this works totally fine if you take spec K to be the algebraic closure of the function field of X, if say X is irreducible. So that gives you a geometric point of X whose image is the generic point of X. And now here U bar will be some other geometric generic point. right? It'll be an algebraic closure of the function field of a component of U, for example. Okay, so that's a perfectly legal operation. Okay, so this is the definition. It's just, maybe it looks a little complicated, but you should think it's really just the same as the usual definition for sheaves on the Zariski topology.
Hey Daniel, sorry, it's pixelated again. In the direct limit there, what is next to the capital U?
It's U comma little u. So, or maybe I should call it little u bar. So it's this geometric point. So we're taking the direct limit over pointed étale X schemes.
Okay, thanks.
Yeah, let me try to stop sharing and start sharing again, since it seems to be acting up. Is that better?
Yes, thanks.
Great. Okay. Cool. So let's take some examples. Okay, so suppose first F is just the constant sheaf Z mod LZ, and X bar inside of X is any geometric point. So can anyone tell me what is the pullback of the constant sheaf Z mod LZ to a geometric point?
Just Z mod LZ over.
Yeah, it's just Z mod LZ. I mean, it's as a set. That's right, or just an abelian group. This is landing in sheaves of abelian groups on X bar. Okay, so why is that? It's not totally obvious, right? So suppose you took a étale X scheme U, which had like more than one connected component, then this F of U here would actually be a product of copies of Z mod LZ, right? It would be a Z mod LZ to the number of connected components. But the point is that given any such thing, you can find a U prime over it, which is connected with the point lying over the point, which like picking out one of your components of your disconnected guy. So every time you have the point, another way of saying that is that the U comma U bar in this diagram, which are connected, are cofinal. Yeah. So anytime you have a cofinal diagram inside of your diagram, the colimit will only see that cofinal diagram. Okay, so if you, sorry, that was a little bit of a fancy way to say it, but you can really prove this by hand. It's not too bad. Okay, so what about another example? So what if F is OX étale? So the étale version of the structure sheaf. So remember, if we had any quasi-coherent sheaf, we made out of it a sheaf on the étale site. So can anyone tell me what is the pullback of this? So it has a name. If you might not have seen it before, depending on what sort of commutative algebra preliminaries you've seen. But I'm curious if anyone knows what this is.
I haven't seen this before, but I have Wikipedia'd it. Is it the Henselization?
So I think it's the strict Henselization.
Okay.
Right. So yeah. So that's the, if I haven't said what to do if we don't have a geometric point here. So I think if you put a point which was not a geometric point, you'd get like if you put an honest closed point of your scheme or an honest point of your scheme, you'd get the Henselization. But because we're taking a geometric point, we get the version of that with the algebraically closed residue field. Right, which is so this is, I think it's called OX X bar strict Henselization. Does that sound familiar, Ollie?
That sounds familiar. Just for an example, if let's say your X is spec Z and your little x is like spec of FP bar or something.
Yeah.
So then we would get ZP?
No, that's not quite right. So that's a complete local ring, right? So this doesn't give you a complete local ring. So first of all, it gives you something with algebraic closed residue field. So one way of saying it is you would take Z bar, so the ring of integers in Q bar, and then invert everything which is not invert everything which is not in the prime ideals, which is not doesn't divide P. Does that make sense? So you get this very big subring of Q bar, actually. Like a big local subring of Q bar.
Because and the reason is you can express that as a direct limit of things where P is everything except for P is inverted.
That's exactly right. Yeah. Well, it's not everything except for P, but yeah, like some collection of things away from P is inverted. Yeah. So what is an étale Z scheme? It's like a finite extension of Z, a finite extension of one way of writing it is you can take a finite extension of, a finitely generated extension of Z. So like invert some primes and then take a finite separable extension of that, or like take a finite extension of Q, take its ring of integers and then invert the primes where it's ramified. And here you're doing that, and you're fine as long as that extension is not ramified at P, right? That gives you something which is étale and also has X bar in its image, right? So you take the kind of union of all extensions of Z which are not ramified at P.
Got it, thanks.
Yeah, okay, so those are the kind of main examples. Okay, are there any questions about that?
What is the exact definition for a ring to be strict Henselian?
I think it's Henselian with algebraically closed residue field.
Okay, so what was the definition for a ring to be Henselian?
Yeah, so it's basically that Hensel's lemma is true. So if you have a monic polynomial and it over the residue field and it factors, then you can lift that factorization over the whole ring.
Okay, yeah, that makes sense.
Yeah. But but here you can that doesn't tell you the definition of the Henselization or strict Henselization of a ring, and the definition is this direct limit. Or this is the definition of the strict Henselization of a ring. Okay, and what is the definition of the Henselization? It's just if you replace this U bar, this geometric point U bar with an actual point, like with the spec of the residue field, including into the ring, and same with U bar. Okay, so but I'll discuss that later. Yeah, I made the choice to not discuss Henselization early in the course, even though it is, I think, traditionally in an étale homology course, like one of the important commutative algebra preliminaries. So this was my cheap way of somehow defining it without telling you about the underlying commutative algebra. Yeah. So in fact, later today, or maybe early tomorrow, depending on how far we get, I'm going to implicitly use a commutative algebra fact about tensor products of strictly Henselian rings, and I'm not going to prove it because I'm trying to skip these sorts of commutative algebra things. But you'll see. Okay, so what do we use stocks for in like usual theory of sheaves on a topological space? I'm going to now tell you a bunch of results about things we can check on stocks. So here, sometimes people call this set the stock of F at X bar. Okay, and I want to convince you that these really behave like stocks. So Jose says, yeah, so we can check, for example, if you have a morphism of sheaves and it's an isomorphism on stocks, then it's a isomorphism. Yeah, and a generalization of that, Benjamin writes in chat, is that we can check exactness by checking exactness on stocks. That's exactly right. Okay, so here's a lemma, which more or less, well, it says at least part of that, and then we'll say the rest of it in the next lemma. So suppose F and G are sheaves of abelian groups. On X et al. Then the following are equivalent. So one is that F maps to G is an epimorphism. 2 is that F maps to G is locally surjective. So what does this mean? This means that given a section S in G of U, there exists a cover, U prime to U, such that S restricted to U prime is in the image of some S prime in F of U prime. So maybe given a section of G, you know, maybe you can't actually hit that section from F, but after refining the object you're on, so after passing to a cover, you can. Okay, and then 3 is that Fx bar to Gx bar is surjective for all geometric points X bar to X. All right, so let's actually prove this. Okay, so can anyone explain to me why locally surjective implies that the morphism is an epimorphism?
Isn't that just the sheaf condition?
Yes, you have to use the sheaf condition somehow, but somehow you also have to use the definition of an epimorphism, right? So what do we have to check?
It's given two morphisms from G into some other sheaf.
Yeah. So what we have to do is we have to say that if F to G, so suppose we have two morphisms like this, H, such that the two compositions agree. Let's call this A and B, then A equals B. So that's what it means to be an epimorphism. So maybe can someone verbally just say, I mean, Arvind, you had the right idea. Can you say how we know this?
Sorry, I can't read after you say agree.
Yeah. So we have two morphisms like this, so that the two compositions agree. Then we want to show that A equals B. That's the goal. Then we maybe I'll write. Then we want A equals B. Yeah. So Benjamin says it suffices to check they agree on some cover. Yeah. So let's try that. So let's take some S. I'm gonna maybe just give this proof verbally. So let's take some S, which is a section of G on U, right? What we want to know is that A of S and B of S are the same thing, right? Yeah. So exactly. So by 2 here, we can replace U with some U prime so that S comes from over here, right? But then we know that if we're coming from F, we know that S prime goes to the same thing in H. Okay, and now where S goes is determined by where S prime goes because U prime was a cover of U. So it's just the same proof as for usual topological spaces. All right. Are there any questions about that? I know I went a little fast, so if there are, you should definitely stop me and ask more. And what I'm trying to convince you with this proof is that we can really reason just like in the usual case of topological spaces. There's nothing really special about these sheaves on sites. Okay. So oh, sorry. Was there a question? I heard some shuffling. All right, so let's do now 2 implies 3. Well, actually, let's do 1 implies 3. All right. So anyone have any ideas? So we want to show that if we have an epimorphism, then this map of sheaves is not, this map, then the map on stalks is surjective for every stalk. Does anyone remember how to do this for sheaves on a topological space? All right. Well, let's assume let's use a proof by contradiction. So assume that fx bar, gx bar is not surjective. For some x bar. So we want to get a contradiction from this. So let's suppose it has co-kernel gamma. Or co-kernel, I think I'm calling it lambda in my notes. Okay, so any ideas? Well, what do we want to do? We want to go from this non-surjectivity, so the non-zeroness of the co-kernel, to showing that f to g is not an epimorphism. So we want to make map two morphisms to some sheaves, which are different, but which agree when you compose with the map from f to g. So in other words, we want to construct some contradictory sheaf out of lambda. Any ideas?
Just skyscraper?
Yeah, exactly right. Yeah, so we're going to consider the two maps from G to the skyscraper sheaf associated to lambda. So one of these maps is just going to be 0, right? That's a map you can always write down. And the other one is going to be the natural map. Okay, so what do I mean by the natural map? I mean, take a section to G and then look at its stalk. And that gives you a map. So, okay, so you have to actually use the definition of the stalk to define this, but you should convince yourself that, like, just like in the topological setting, it makes sense. Okay, but now lambda was the co-kernel of the map on stalks. So that means that both compositions are going to be 0. Okay, and this is a contradiction. Okay, right, because if both compositions are 0, then this lambda itself has to be 0. All right. Are there any questions about this? All right. So now let's do 3 to 2, and then we'll be done. Okay, so maybe can anyone verbally explain this one to me? So suppose the map on stalks is surjective, then we want to show that this map of schemes is locally surjective. So here we're actually going to, sorry, this map of sheaves is locally surjective. So here we're actually going to use something about the étale topology. And so far, I mean, this 1 to 3 sort of used something, although you can really generalize it. Here we're really actually going to use something about the underlying geometry. So can anyone explain 3 to 2? So I want to say, given us a local section to G, I want to say that I can maybe, after passing to a cover, show that it comes from F. And what do I know? I know that the map on stalks is surjective. So how would you do this for topological space? So the usual proof just works. So let's start. So let's suppose
surjective homomorphism of direct limits.
Yeah, that's right. So can you say more? So given S and G of U, we want to find some U prime so that S comes from F. So S restricted to U prime comes from F. So, okay, so how do we find such a U prime?
We just take a geometric point of view.
Yeah, so let's just take a geometric point of view. So we know the map is surjective on stop. So we just pick one. So choose X bar and U. So we know that Fx bar to Gx bar is surjective. So this means that there exists some étale neighborhood of X bar, let's call it V, with a point V bar. So what do I mean by an étale neighborhood? I mean an étale map to X, which is pointed by some V bar, so that V bar maps to X bar, right? So just like a diagram, exactly a diagram like this from before with U replaced with V. So what does this tell us? So these direct limits are surjective. So we know there's something like this, such that S restricted to V is in the image of F. Great. Okay, so what now? Are we done? So I claim we're not done. Does anyone see why we're not done?
Yeah.
Yeah, so Benjamin in chat says we need to extend V to a cover, right? So V is not a cover of U. It's just an étale thing mapping to U. Okay, so how do we extend V to a cover?
Do the same thing with a geometric point not in the image.
Yeah, exactly right. So now choose X bar prime not in the image of V and keep going. Okay, and you just keep adding étale opens to your cover until they're actually a cover. Okay. Are there any questions about that?
This seems strange. I mean, it looks like this won't work if we don't have the axiom of choice. Is that correct?
It looks like this won't work if we don't have the axiom of choice. I don't think so. So because we're only choosing, yeah, how should I say this? We're only choosing elements of sets that we can assume to be non-empty, right? So let's just choose our first X bar. Well, suppose U is empty. Like, so suppose there's no geometric point. Well, okay, you need the axiom of choice to make a geometric point in the first place, right? To make a spec K, right? To make an algebraic closure. But let's ignore that issue. So let's suppose we're working over, let's say we're working over varieties of an algebraically closed field. So we don't need to worry about that. You could also avoid that issue too, but let's not with what I've told you so far. So let's just choose an X bar. Well, if U is empty, we're done. So we know U is non-empty, so we can choose a point, right? Now that gives us a V. So suppose V. So let's look at the complement of the image of V. Well, if that's empty, we're done, right? So we know it's non-empty, so we can choose a point. So I think when you're in that situation, you're not actually using the axiom of choice to make a choice. Right?
But
yeah.
Don't you need choice to finish for proof? So like to know that eventually this will terminate?
I don't think you need it to terminate. Right? You can just take the union as you keep going.
Yeah, but
I guess
we need it.
Let's actually think through it carefully. So if you assume your scheme is quasi-compact, then you know it terminates from quasi-compactness. If you don't assume that, then you'll need some kind of transfinite induction, and then yeah, you'll probably need choice. Right? Maybe I shouldn't say you need choice, but at least this proof will use choice.
I've also got a question regarding that.
Yeah, go ahead.
How do you know that the morphism is still étal if you take the disjoint union?
Yeah,
Or the
so
infinite union?
atalness is a local property on the source. So if you take the union of two atal morphisms, that's atal. And that you can see, yeah, so what, yeah, so maybe what you need to check is that it's locally a finite presentation. Well, that's a local property. And then it's unramified, and that's also a local property. And that it's flat, which is also a local property. Does that answer your question, Nicholas?
Yeah, I think so. Maybe I thought it was had to be a finite presentation.
Yeah. Yeah. Any other questions? Okay. Cool. All right. So so okay, so what have we checked? So we've now checked that we can check surjectivity on stocks. So let's take a 2-minute break and then we'll do injectivity. Yeah, so maybe during the break, are there any other questions?
Yeah, I have a quick question.
Yeah, go ahead.
Instead of looking at, pullbacks over geometric points.
Yeah.
So something changes if we look at a non-geometric point, right? Like just some spec of K. Like
Yeah, so the main issue is that sheaves on a non-geometric point are not just sets anymore.
Because they
So I think probably next time we'll talk about sheaves on spec K.
Cool.
Yeah, so they're related to they're I'll just spoil the punchline line. They're the same as discrete G modules where G is the Galois. So that's it's a little bit more complicated. And right now, I mean, I don't think it would be too hard to show that the pullback to a non-geometric point is actually a sheaf, or like that it can be sheafified. But we at least in principle don't have the technology to do it yet. Sophia asks, can we think of the gamma we defined for cohomology as pushed forward onto a point? Yeah, that's a good question. So if we have X over spec K bar, spec K, where this is algebraically closed, then let me call it, maybe let me call the structure morphism pi, then pi star is just the same as gamma. Using the identification between sheaves on an algebraically closed spec of an algebraically closed field and sets. If K is an algebraically closed, it's not quite the same thing. So if we have X to spec K, then pi star, what does it do? It sends sheaves on X to sheaves on spec K, and those aren't just sets. So so it's not actually the case that like it doesn't make sense to identify global sections with push forward. But what you can say is that if you take the global sections on spec K of the push forward of a sheaf F, that's the same as taking the global sections on X of your sheaf F. Okay, so there's still a relationship. Does that answer your question, Sophia? Okay, great. Yeah, so over an algebraically closed field, it really is the same thing, but over a non-algebraically closed field, there's sort of functors between, like the target categories of the functors are not the same. All right, great. Okay, so let's do another lemma. So we've said that surjectivity can be checked on stocks. Now let's just do exactness in general. So suppose 0 to F to G to H is an exact sequence of sheaves on, sorry, let's say it's a sequence of sheaves, is a sequence of abelian sheaves on exciton. Then the following are equivalent. So one is that the sequence is exact. So two is that if you take sections, this is exact for all u. Okay, and 3 is that the exact sequence on stocks is exact. Here for all geometric points. Okay, so let me just say a word. I mean, so maybe it's not even obvious what the difference between 1 and 2 is here. So what does 1 mean? So 1 means that the map from F to G is a monomorphism, and moreover that it's the kernel of the map from G to H, which means the equalizer of the diagram, which is 2 maps from G to H, where one is this map and the other one is the 0 map. Okay, so that's what 1 means. So 2 is I hope it's clear what it means, and 3 I hope it's also clear what it means. Okay, are there any questions about the statement of this lemma? So let me just remind you. So this means that F is the equalizer of the diagram G to H, where let me give this map a name. It's called little f, where this is little f and this is 0. Okay, so that's what this means. Okay, and I'm actually going to leave the proof to you as an exercise. And the reason why is it's just like the last lemma. It's just exactly the same. It's the same exercise for topological spaces. All right. But maybe I'll just verbally to see that. Like, so maybe can anyone explain to me why 2 implies 3? So my claim is that this is the same proof as for topological spaces. Just as an example, to see 2 implies 3. Well, how do we get the sequence in 3 from the sequence in 2? You just take a bunch of direct limits, right? And direct limits preserve exactness. Okay, so you should convince yourself of this, that it really is the same. All right, so now we can actually, are there any questions about that? Okay, so now we can actually prove sheafification exists. Exists. So here this is for pre-sheaves on Exatal. So let me remind you of the statement of the theorem we're trying to prove. So we have a forgetful functor from sheaves on Exatal to pre-sheaves on Exatal, and we would like to show that functor has a left adjoint, which means we want to construct for any pre-sheaf, we want to construct a sheaf so that a map out of that sheaf into another sheaf is the same as a map from your original pre-sheaf into that sheaf. Okay, so step 1 is we're going to construct a version of the espace étalé. So we're going to construct an espace étalé. So does anyone have any ideas? I'm curious. So here we're actually going to use the axiom of choice if you like. So for each point X in X. So this, I mean, a literal point of the topological space. We're going to choose a geometric point. X bar lying over X. So what do I mean? I mean, take the residue field of our point X and take an algebraic closure of it. Now, now given F, which is a presheaf on X et al., I'm going to define what I'll call the espace étalé of F, so esp of F. So what is it going to be? It's going to be the product over all our geometric points X bar of the skyscraper sheaf associated to the stalk of F at X bar. Okay, strictly speaking, I think I only defined a stalk for presheaves, but you can take the exact same definition for a sheaf. Okay, there's a natural map. So this thing, by the way, this is a sheaf, right? Do you all agree with this so far? Or does anyone disagree? Or have a question as to why this is true?
So you're saying esp is a sheaf?
Yeah, esp is a sheaf. So here are all these guys. So fx bar it's just a set, right? So that's the same as a sheaf on spec k bar. And then push forward sends sheaves to sheaves. So the skyscraper sheaf is a sheaf. And then a product of sheaves is also a sheaf. And that I haven't proven for you, but it's sort of immediate from the definition. Right, what is a section to a product of sheaves? It's just a product of sections. And then you check that each of those sections is defined locally. Right? So there's a natural map of presheaves from F to this, what I called esp of F. And what is it? Well, you just take a section of F and you send it to its germ, and you send it to its value in each of the stalks. Okay, and then we're going to make the following definition, which is Fa. So this is the sheaf associated to the presheaf F, is the subsheaf of esp of F generated by F. So what do I mean by that? So what do I mean by that? I mean that Fa of U inside of esp F of U is the set of S in esp F of U, which are locally, so such that S is locally in the image of F. So here you should think of this as here, this is like the product of all the stalks, and then Fa of U is like the espace étalé living inside of that thing. So this is exactly how you construct the espace étalé in the case of usual sheaves on a topological space. Okay, so claim one. So we need some claims. So claim one is that Fa is a sheaf. So can anyone explain to me why this is true?
Can you just zoom in on the right side of the set?
Here, so it's just that S is locally in the image of F. So what do I mean by that? So let's take a section to F of U. So what is that? That's like a product of it's like a, for every geometric point of U, that's like a element of the stalk of F. And then I say that section is in Fa, if you can refine U, so if you can take some U prime to U, so that it's in the image of this natural map from F to S of F. Okay, can anyone tell me why this is true?
Well, it's separable because it's a subsheaf of a.
That's right.
Well, it's a pre-sheaf of. Yeah.
Well, yeah, it's a subfunctor of a sheaf. Yeah, that's right. So it's a subfunctor of a sheaf. So separable means that the map in this equalizer diagram is injective, right? So that a function is a section is determined by what it is locally, and that's true for S with F. So it's true for FA. All right. So what about why can you glue?
Because of the second part in the thing that is like we were saying that is locally defined on.
Yeah, that's exactly right. Yeah. So this is almost a tautology. Okay, and then 2 is to check that FA is actually left adjoint to the forgetful functor. Okay, and this is an exercise. So my general rule here is that I'm not going to prove something if the proof is the same as it is for topological spaces, and this really is the same as the proof for topological space, for sheaves on topological spaces. Yeah, but this is again an exercise that you like really have to do if you're following the course. All right, are there any questions about that? Yeah, so Sophia asked, did you mention that you need to perform this operation twice to get a sheaf? So not this operation. So this is kind of a trick. So this is a way of getting a sheaf out of a pre-sheaf, which only works on sites which are sufficiently geometric. So what we really used here is that that there are enough points. So we use all these geometric points. So what's true in general is that for any site, the forgetful functor from sheaves to pre-sheaves has a left adjoint. And here we used symmetrical geometry. We used the existence of honest points to construct our left adjoint. So this proof won't work in general. So for the general statement, so for an arbitrary site, there's some weird plus operation. And in order to turn a pre-sheaf into a sheaf, you have to perform that plus operation twice. But that's a different argument. Yeah. Yeah, I agree. It's cool. Okay. Cool. So okay, so you should really do this exercise if you haven't thought about it before. Okay, so let's immediately get some corollaries out of this. So a corollary is that colimits exist in the category of sheaves on exciton. So can anyone explain to me why this is true?
Well, colimits exist for pre-sheaves.
Yeah.
And then I just sheafify.
Yeah. So step 1 is to observe that colimits exist for pre-sheaves. So here, this is sheaves of sets when I write sheaves, or sheaves of abelian groups. So colimits exist for pre-sheaves. So why is this? Well, colimits always exist for functor categories valued in a category where colimits exist, namely like sets or abelian groups. So why is that? It's because you can compute them pointwise. And then step 2 is that left adjoints send colimits to colimits. So in particular, yeah. So how do you take the colimit? So the colimit of some fi, here I is in some diagram I, is just it's just going to be colim here in the category of pre-sheaves of the fi, and then sheafify that. Okay, so why do left adjoints send colimits to colimits? So if you haven't seen this before, you should figure out why it's true. But the reason why is that a colimit is defined by a mapping out property. And if you have a left adjoint, the definition of a left adjoint is that you know how to map out of it. So that's why. Okay, so now the corollary is that that sheaves on XHL is in a, so here, when I write sheaves now, I mean abelian sheaves, is in abelian category. Okay, can anyone tell me why this is true? So we need to check a couple things to check this. So what do we need to check? Yeah, so we need to check finite products. So yeah, so finite products, so products and kernels and this sort of thing, we knew because we could define them by hand, pointwise. So we need, so limits exist because we can define them pointwise. Okay, we need co-kernels. So now we know co-kernels exist because co-kernels are co-limits. So let me just remind you why that is. So the co-kernel of a map from F to G is just the same as the co-equalizer. So a co-limit of the following diagram. So let's call this map little f. Okay, and then we need to check one more thing. Yeah, so what is the other thing we need to check? Yeah, so every epi is a co-kernel. So I think the maybe one way to say it is that image equals co-image. I think this is actually this. I think every epi is a co-kernel follows from this. So here, there you can take the co-kernel of a kernel or a kernel of a co-kernel. Okay, and this you check on stocks. Okay, and I'll leave that to you as an exercise. Cool. Okay, so we're almost to defining sheaf cohomology. Oh, we're out of time, unfortunately. All right, so we're out of time. So next time we'll actually finish proving that injectives exist. So next time, injectives. We'll define cohomology, and then we'll actually start computing. So I'm gonna develop the basics of check cohomology for HL cohomology, and then hopefully by next week, we're actually gonna really start like computing the HL cohomology of a curve, and we'll be out of this formal business. All right, so let me stop recording.